Hi my dear friends, welcome back to our YouTube channel ADC Maths. In this video we are going to discuss the steady state with non-zero boundary conditions. Non-zero boundary conditions. You see, once we have zero boundary conditions only, we are able to determine or eliminate the unknown arbitrary constants is available in the correct solution. It's a non-zero boundary conditions. What we can do? Yeah, we can convert those non-zero boundary conditions into the zero boundary conditions by using some techniques. So in this video, we are going to discuss how we are going to convert the non-zero boundary conditions into the zero boundary conditions. So in this problem, what I have considered a bar of length 10 centimeter, that is L equal to 10 centimeter, and the temperature at this end x equal to 0, it is named as A, is 20 degrees Celsius, and at the end B is 40 degrees Celsius until the steady state conditions prevails. So under the steady state conditions, the temperatures are 20 and 40. So 20 in the left hand end and 40 into the right end. And the same time this was insulated laterally so that the temperature does not come out about this side, the middle of the part. So only we have to measure the temperature at the end sides. So 20, 40. So this is the first stage. It's called the initial state, or is often called as steady state. Later on, what will happen? The temperature at the end A is then suddenly raised to 50 degrees Celsius, and at the same instant that the temperature at the other end, the B end, is from 40 degrees Celsius to, it is reduced to, is lowered to, it is decreased to 10 degrees Celsius. And once it will reach us the 50 degrees Celsius in the left hand side and 10 degrees Celsius in the right hand side, they will again maintain both the temperatures. So this is the second stage of steady state. This is the second stage of steady state. This is the first stage. Initially, the first stage of steady state is 20-40, and it can be raised to 50 and it can be lowered to 10. Again, it will be maintained. So it is non-zero. That's why the title is called non-zero boundary condition still. Isn't it? Initially 20-40, now it is 50-10. So this comes under non-zero. Still it is the steady state. That means that it will maintain the temperature 50 in the left hand and 10 in the right hand. Right? So in the between 20 to 50 and 40 to 10, what happened? 20 to 50 and 40 to 10, there may be some changes in the temperature side with respect to the time t. Now that state is called the transient state. It is called the transient state. It's called unsteady state. So once we are going to determine the complete solution, that is called the temperature distribution function of the bar, once it will reach us from 20 to 50, 40 to 10, then we can consider two cases. One case for the second stage, initial state, that means at 50, 10 and plus the transient state. Because what is called transient state? Yeah, it can be raised the temperature from 20, 20.5, 21, 21 point, like that. So it will be raising. The temperature is varying with respect to time t. Once it will reach us 50, it will be maintained. It's called steady state. Similarly, in the second end, from 40 to 39.9, 39.8, 39, 35, 36. So it is gradually decreasing. So that decreasing means that temperature is varying with respect to time t. That is called the transient state. Once it will reach us the 10 degrees Celsius, it is maintained. It will be steady. That is called the second stage of steady state solution. Now my aim is to determine what is the first stage of steady state. Then let us move on to the second stage. When we move on to the second stage, there are two solutions. One is second stage steady state and plus the transient state. So let's move on to the question now. See that this is the question now, right? Until the steady state conditions prevail, this is 20-40, and the temperature is suddenly raised to 50 degrees Celsius, and at the same instant that it is lowered to 10 degrees Celsius at the end B. So what will be the temperature distribution function? So that's why this is comes under steady state with non-zero boundary conditions. Our ultimate aim is to convert the non-zero boundary conditions into the zero boundary conditions. Let us see how we are going to achieve our goal in this problem. So I can consider the first initial stage. What's the first initial stage? That is called the initial temperature distribution. Initial temperature distribution is often called as the steady state solution, right? How to get this one? Yeah, and at the initial stage the temperatures are u of 0 is equal to 20 degrees Celsius and u of 10 is equal to 40 degrees Celsius. As we know that what is the steady state solution? The steady state solution is, please go and watch my previous videos. I have derived separately the steady state solution from the one-dimensional heat flow equation. Please go and watch my previous video. It's nothing but u of x is equal to ax plus b. So this is my equation number 1. Let us use this condition number 1 here. By using the condition number 1 in equation number 1, we get u of 0 is equal to a into 0 plus b is equal to, the temperature is 20 at the time. So from this we get b is equal to 20. Now use the second boundary condition in the equation number 1. We are getting that u of 10 is equal to 10 into a plus, what's the b value? From the previous step we get b equal to 20. At that time the temperature is 40 at the right hand side. So by that way we get 10a is equal to 20, otherwise a equal to 2. So this is the a and the b value at initially. So at initially, what is my steady state solution? U of x comma 0, because initially means time t equal to 0, ax plus b. Now a equal to 2, b equal to 20. So 2x plus 20 in between the rod, the bar 10, 0 to 10, 0 and 10. So this is the boundary value, the boundary condition at initially the temperature distribution under the first stage of steady state. So later on what happened? The temperature at the end A is raised to 50 degrees Celsius. Isn't it? Let us see once again, this is non-zero. Let us say this is non-zero. This is not 0, 1, this is non-zero. So under the second stage, what happened? The boundary conditions are the boundary conditions of u of x comma 0, that is 0 comma t is equal to 50 degrees Celsius and u of 10 comma t is equal to 10 degrees Celsius. So this can be maintained 50 and 10. So this is the second stage of steady state. And what about the initial temperature distribution? This is nothing but what we have get from the first stage, u of x comma 0 is equal to 2x plus 20 in 0 less than x less than 10. What about here? For all the time t greater than equal to 0. For all the time t greater than equal to 0. So this is once again comes under non-zero boundary conditions. Once when we have this non-zero boundary conditions, then it is very tough to find out the unknown constants that are available in the correct solution. Here it is, remember what is the correct solution for the one-dimensional heat flow equation? Is a cos px plus b sin px into e to the power minus alpha squared p squared p. So this is my correct solution, is named as equation number 2. Alright. Now can we substitute the condition number 3 here? What we will get by putting x equal to 0, cos 0 is 1, so a, sin 0 is 0, so e to the power minus alpha squared p squared t is equal to how much? 50 degrees. So it is 50. And what about by using the condition number 4? When x equal to 10, I am getting a cos 10 into p plus b sin 10 into p into e to the power minus alpha squared p squared t. At this time the temperature is 10, so it is equal to 10. So to see that from this equations it is unable, it is very difficult to determine the a, b and the p value, because the product of a into e to the power minus alpha squared p squared t equal to 50. That means that which one is 50 and which one is, what is the value for a, what is the value for p, we don't know. Similarly the second equation, a cos 10p plus b sin 10p e power minus alpha squared p squared equal to 10. So it is very difficult task to determine the constants a, b and p from this stage. So that's why what we are doing, that we are going to split up this stage into two. What are they? How? I can divide the u of x comma t is equal to, once it will be raised from 20 to 50, it is standby, that means steady. From 40 to 10 it is steady. So I can get the second stage of steady state solution 50 10, right? And in between that time 20 to 50, 40 to 10, there may be some time gap, there may be some changes in the temperature with respect to time t. Now that state is called transient state. So the transient state solution is called ut of x comma t, because the time factor is involved. The time factor play a role here, because from 20 to 50, how much time will take to reach 50? Similarly, that case. So once it reaches 50, 10, it will be steady. So that's called second stage of steady state equation. So this is my equation star. Now my aim is to find the steady state and the transient state solution. How to get the steady state? So I go with the first concept. The first concept is the first stage to find out the steady state solution. What is this steady state? At this moment, the temperature, at this moment, the second stage, the temperatures are 50 and 10. So that the condition number, boundary condition number 6 is us of 0. When x equal to 0, the temperature is 50 and 51 is 7 to 1. That is us of 10 is equal to 10. So there are two more boundary conditions. We have 50 and 10. So as we know that, what we know, us of x, the steady state solution, is cx plus d, because already I used ax plus b for the first stage of initial state. So this time I go for cx plus d. Now can we apply the condition number 6 by putting x equal to 0? us of 0 is equal to c into 0 plus d is equal to 50. So by that way d is equal to 50. What about the seventh condition? By putting x equal to 10, we get us of 10 is equal to 10c plus d, d equal to 50 is equal to how much here? 10. So by that way it is nothing but c is equal to minus 4. C is equal to minus 4. Is right, sir? So by this way we get the us of x. What's the us of x? The second stage of boundary steady state conditions under 50 degrees Celsius, under 10 degrees Celsius, the temperature distribution is minus 4x plus 50. Minus 4x plus 50. So the first stage I use 20 40, I get the 2x plus 20, right? The second stage I use 50 10, I use now minus 4x plus 50. So almost I use 20 40 50 10, that's it. Almost is over. So from these two I find out these two steady state solutions. But what about the transient state? So how to get the transient state? If we need to get the transient state, it's a function of x and t. It's a function of x and t. So what will be the complete solution or the correct solution of the transient state? Is a function of x and t. That means that ut of x comma t is equal to, once again, a cos px plus b sin px and e power minus alpha squared p squared t. So we need to determine a, b and p. So once we need to determine the a, b and p, we need at least some zero boundary conditions. Okay. So normally the boundary conditions are based on x and t. The first boundary condition for the left end x equal to 0. The second boundary condition for x equal to 10. And third boundary condition for t equal to 0. So these are the three conditions. So let us use this technique to determine the new set of boundary conditions for the transient state solution. How to get the new set of boundary conditions, that too particularly already I have used almost all the non-zero boundary conditions. So this time I need some zero boundary conditions. This time I need some zero boundary conditions. Then only we are get the unknown constants in the ut of x comma t, a cos px plus b sin px into e power minus alpha square p square t. So let us find the boundary conditions. How we are going to get these boundary conditions? Let us see. So from the hash equation, what we will get? From the star equation, I think what's the star equation? U of x comma t is equal to us of x plus ut of x comma t. Isn't it right? Right, sir? So this can be named as equation number 3 now. So by that way, what is ut of x comma t is equal to us of x minus u of x comma t. So I can rearrange this one. So this is my equation hash. Our aim is to determine ut of x comma t, but for that I need some zero boundary conditions. So I can get those boundary conditions, particularly the zero boundary conditions, from the hash equation. Can I substitute the x is equal to 0 in hash and put in the first boundary condition? Ut of 0 comma t is equal to us of 0 minus u of 0 comma t. U of 0 comma t. Can you tell me what is us of 0? I think so. Us of x already have second stage minus 4x plus 50. Now substitute x is equal to 0. Substitute x is equal to 0 in this equation. We get it is 50, right? Minus what is u of 0 comma t? U of 0 comma t from the third boundary condition, it is 50. So 50 minus 50 is 0 because this is the second stage. In the second stage, the left hand side temperature is 50, right hand side temperature is 10, right? And what about the right hand side? When x is equal to 10, the corresponding ut of 10 comma t is equal to is us of 10 minus u of 10 comma t. Now get the us of 10 by substituting x equal to 10 in this equation. We get minus 4 into 10 minus 40 plus 50 is 10 minus what about u of 10 comma t? U of 10 comma t is in the second stage of steady state temperature 10. So 10 minus 10 0. So actually it will be automatically converted from non-zero boundary conditions into the zero boundary conditions. What's the third boundary condition? The third boundary condition is when t equal to 0. When t equal to 0, ut of x comma 0 is equal to us of x minus u of x comma 0. So this is equal to, what about us of x? This one minus 4x plus 50 minus, what's the u of x comma 0? This one, it is 2x plus 20. So minus 4x minus 2x minus 6x, 50 minus 20 is 30 plus 30. So otherwise you can take minus 6 outside, x minus 5. So these are the three new set of boundary conditions. Let us apply this one by one in the equation number 3. So what about the new set of boundary conditions here? The new set of boundary conditions are, the first one is the 8th condition. It is ut of 0 comma t is equal to 0, and the 9th condition is ut of 10 comma t is equal to 0, and the 10th condition is ut of x comma 0 is equal to minus 6 into x minus 5. Is it right? Is it right, sir? May I write, sir? Is it right? I think so. In this hash equation, we will get is ut of x comma t is nothing but u of x comma t minus us of x, isn't it? I made a mistake here because of, I can fix here ut of x comma t, so it is come to this side. So this becomes the reverse order, u of x comma t minus us of x. But anyhow, when x equal to 0, there is no change, 50-50 only, 0, 0. And for 10 is also there is no change, 0. But when it's put t equal to 0, what happened? This becomes u of x comma 0 minus us of 0. So that means that we get it is 2x plus 20 minus of minus 4x plus 50. So that way get 2x minus plus 4x is 6x. 20 minus 50 is minus 30. So we get 6 into x minus 5. Actually here I am getting minus because of the reverse order. So this is the right answer, because in this hash equation ut of x comma t equal to u of x comma t minus us of x. So that's why I get the reverse order. But anyhow, there is no major changes in the first two boundary condition. The third one, there is a plus sign actually. It's a plus sign. So this is the right idea. So by this we get the 10th equation is plus 6 into x minus 5. Thank you. Yeah, now let us apply the conditions 8, 9, 10 in the equation number 3. What happened? So when I use the condition number 8, by putting x is equal to 0, in equation number 3, I am in that a cos 0 is 1, sin 0 is 0, e power minus alpha squared p squared t is equal to 0. Now the return temperature is 0, so this is comes under 0 boundary condition, right? So by that way, either a equal to 0 or e power minus alpha squared p squared t is equal to 0. So e power minus alpha squared p squared t not equal to 0, since the minimum value for t is 0. So that's why a equal to 0. So what about the ut of x comma t now? Ut of x comma t is equal to b into sine px e to the power minus alpha squared p squared t. This is equation number 4. Now use the second boundary condition when x equal to 10. When x is equal to 10, we get, by putting x is equal to 10 in equation number 4, we get b into sine 10p e to the power minus alpha squared p squared t is equal to 0. So once again, b is equal to 0 or sine tp equal to 0, 10p equal to 0 minus e to the power minus alpha squared p squared t equal to 0. So this is not equal to 0, b not equal to 0, because of once b equal to 0, we get the trivial solution. So by that way, sine 10p is equal to sine n pi. So p value is n pi by 10. So when I substitute p value in this equation number 4, we get the most general solution ut of x comma t. So by combining all possible solutions, we may get bn into sine n pi x by 10 e to the power minus alpha squared n squared pi squared t by 10 squared is 100. So this is my ut of x comma t. Already we know us of x. So still we need to find out the bn. How to get this bn value? Use the 10th boundary condition. By putting t equal to 0, we get the required bn. So this is the final stage. When I substitute t equal to 0, what happened? When I substitute t equal to 0 by using the condition number 10, by putting t equal to 0, we get ut of x comma 0 is equal to sigma n is equal to 1 to infinity capital Bn into sine n pi x by 10 e power 0 is 1 is equal to 6 into x minus 5. So this is the polynomial function. Let us expand this by using the half range sine series. We get sigma n equal to 1 to infinity bn sine n pi x by 10 is equal to sigma n is equal to 1 to infinity small bn into sine n pi x by 10. By comparing both these sides, we will get the capital Bn is equal to small bn. So what's the capital Bn? Capital Bn is equal to small bn is equal to, the formula is 2 by L integral 0 to L f of x sine n pi x by L into dx. But here my L is 10, so the substitute L is equal to 10, we get it is 2 by 10 integral 0 to 10 6 into x minus 5 into sine n pi x by 10 into dx. Let's take the 6 outside. It is 12 by 10. Let us use the Bernoulli formula. What we will get? Let's apply the Bernoulli formula. We get is x minus 5 minus cos n pi x by 10 by n pi by 10, right? Minus 1 into minus sine n pi x by 10 by n pi by 10 to the 4 square. Now the limits are 0 to 10 only. By putting x equal to 10, 10 minus 5, it is 5. So the mean will 10. 6 by 5, it is minus 10 by n pi reciprocal. What about 10 minus 5 is 5 into cos. By putting x equal to 10, we get cos n pi. By here, cos n pi is 0, sin 0, 0. Let's leave it. Now minus, by putting this is minus 10 by n pi is common. Yes, right? Minus 10 by n pi is common here. So what about this is 10 minus 5 is 5 cos n pi. By putting x equal to 0, by putting minus 5 into cos 0 is 1. So I think so minus plus 5, 5 taken outside. So this gives minus 60 by n pi. Cos n pi value is minus 1 whole power n minus 1. So if n is odd, what happened? If n is even. So once the term looks like this, we can discuss about the nature of n. If n is odd, this becomes minus of minus 1 is minus 2 plus 120 by n pi. By putting if n is even, 1 minus 1 is 0. So that's it. So this is the bn value for this one. Can you check the answer? Yeah, minus taken already outside. Minus taken already outside here. Minus 10 by n pi. So 10 minus 5 is 5 cos n pi. Minus is a lower limit. Minus by putting x equal to 0. 0 minus 5 is minus 5. Cos 0 is 1. Minus plus 5. 5 taken outside. Minus 50. This can cancel by 10 times. Minus 60 by minus 1 whole power n. Then this becomes minus of minus plus only. No. Minus of minus is plus here. So this is plus only. So if it is a plus means if n is odd, this becomes 0. Isn't it? If it is odd, n becomes 0. If it is even, this becomes plus 1, 1 minus 1. So 2 minus 1 by 120 by n pi. Slight changes, it becomes a huge difference because minus or minus becomes plus 5. I taken 5 outside. So 50 by 5 is 10. 10 into 6 minus 60 by n pi. This is minus 1 whole power n. Plus becomes here 1. So if n is odd becomes 0. If n is even becomes plus 2. 2 into minus 60 is minus 1 by 20. Minus 120 by n pi if n is even. So finally, what about the ut of x comma t? The substitute the ut of x comma t place in the bn value. We get this for n is equal to even 2 comma 4 comma 6 comma infinity minus 120 by n pi. So this is my ut of x comma t and this is my us of x. So minus alpha squared n squared pi squared t. So finally, my required temperature distribution is us of x. So minus 4x plus 50 plus the ut of x comma t sigma n is equal to the even number 2 comma 4 comma 6 comma up to infinity minus 1 by 120 by n pi sin n pi x by 10 into e to the power minus alpha squared n squared pi squared t by 100. So this is somewhat very lengthy problem because it is the non-zero boundary condition. Because of it is the non-zero boundary condition. Once it is non-zero boundary condition, let us convert this into the zero boundary condition by considering the steady state temperature us of x and the transient state temperature ut of x comma t. So this is the problem based on the steady state with the non-zero boundary conditions. So this is the somewhat is very lengthy. Yes, understand. So thank you so much for watching our YouTube channel ADC Max. Thank you.